All right, class, we're gonna get started. All right, so today we're gonna be deriving Navier-Stokes. Right, so we're gonna be deriving the differential form of the momentum balance, and we're gonna see that when we apply that to a incompressible Newtonian fluid, the resulting set of equations we're gonna call the Navier-Stokes equations. I just wanted to recap where we've been, because we went kind of fast through the end of class on Friday to get to mass conservation. So that's where we're going to start today. But before I begin, any questions? Okay. All right. So just to recap where we were on Friday. So on Friday, we said that we started by tracking mass fluxes through a differential element, right? So this is some small differential element, some small element of the fluid, and we tracked mass fluxes into and out of this element. By tracking mass fluxes and applying the condition of mass conservation, right? Mass is conserved. So we set all of the accumulation within the control volume as well as the net flux in or out equal to 0. We developed this form of the mass conservation equation, right? So it's a little bit different than the control volume form because in this form, we're considering the partial derivatives of the, in this case, the velocity times the density, right, at each point within the fluid. As well as the rate of change of density, again, at each individual point within the fluid. So this would apply if we have, some non-uniform velocity field that's varying spatially within a fluid. This equation should hold, right? This form of mass conservation should hold. And then analogous to what we did in the control volume forms of conservation and balance laws, we asked, what happens when we simplify this? Or how can we simplify this, I guess. And we started out with the incompressibility assumption, right? So we said basically rho is constant. So if rho is not changing in time, this term drops out. If rho doesn't change in space, then it pulls out of all of these derivatives, right? We can pull rho out of all 3 derivatives. And now since this whole thing is equal to 0, we divide through by rho, and we're left with the incompressible flow representation of this conservation law of mass conservation. And we said we can write it as del dot v equal to 0, or in Cartesian coordinates, du dx dv plus dv dy plus dw dz is equal to 0. All right, that is our form of mass conservation for an incompressible fluid. Okay. So a note of potential future confusion here. Note that in this form of mass conservation, it's du dx, dv dy, dw dz. So one thing that I've seen in the past is if I ask a question about, let's say you're eventually going to have to solve for force in x on a fluid, or something in the x direction on a fluid. I think sometimes it's easy to get fixated on just the x component of velocity and then try to plug the x component of velocity in all 3 of these places, and you end up someplace misleading and wrong. So don't do that. So this del dot v operator in Cartesian coordinates means we're taking the x derivative of the x component of velocity, adding the y derivative of the y component of velocity, and then adding the z derivative of the z component of velocity. So let's just consider a 2-dimensional flow where all we have is flow in x and y. Let's say this term dw dz is 0. If we have, this is basically saying that if the fluid is slowing in the x direction, right? So if the velocity coming into this control volume in the x direction is larger than the velocity leaving this control volume in the x direction, right? So the fluid is slowing in this direction. Then that has to be balanced out by the fluid accelerating in this direction, right? Meaning, so if we just consider what's going on in the x direction here, there's more the fluid slowing down implies that there's more volume flow, there's more mass flux coming in through this face than is leaving through this face. And that has to be balanced out somehow. And it's balanced out by there being, in this case, since it's only a two-dimensional flow, it has to be balanced out by more flux leaving in the y direction than enters in the y direction. Yeah. The fluids are mixing. Yeah, I mean, we're assuming this is just a differential fluid element, so it's all the same fluid that's coming in or out of both faces. Yep, that's right. And this is going to be some infinitesimally small fluid elements. And this is dealing with the derivatives of a continuous velocity field. Okay. Okay, so this is directly analogous to what we had for the control volume form, in that for the incompressible flow case, there's no mass, right? There's no density in this form, right? The density dropped out. And so what we're left with only deals with velocities and the rate of change of velocities. So this is like for incompressible control volume form, we said that the sum of the velocities times the areas out is equal to the sum of velocities times the areas in. And again, remember, rho dropped out of the incompressible form of our control volume continuity or mass conservation equation. The same thing is true in differential form. Okay. All right, any questions on this? We're going to move on to momentum next, but any questions on mass conservation? Yeah. Sorry, what's that? Yeah, this is true. So this is true for any incompressible fluid, regardless of what's going on within this control volume. If the let's say if it's just two-dimensional, we're confining ourselves to two-dimensional because we can draw it on the board or on the slide here, right? If du dx is less than 0, dv dy has to be greater than 0 for mass to be conserved in an incompressible fluid, right? Otherwise, we'd be accumulating mass in here. Okay. Yeah, and to enforce, to make sure the mass is conserved, this equation has to be identically 0. Right? Okay. Any other questions on mass conservation? Okay. So, and I believe you have an example on the homework for this week about testing essentially whether or not mass is conserved for a velocity field that I've given you. So you get a chance to apply this. Yeah, question. Well, this just means it's slowing down, right? So this means that as we're increase x, the rate of like u is getting slower, right? So du dx in this case is less than 0. Okay. Okay. All right. So now we're going to move to momentum. And one thing to keep in mind here is that just as with the equation that we developed from the control volume approach, we're going to end up with a vector equation, right? Remember, momentum is a vector, so momentum balance equation is a vector equation. So we're going to have 3 equations, one each in x, y, and z, just like we did for the control volume approach. In this case, we're going to start with Newton's second law and the total derivative. So now we're going to use that total derivative thing that we developed a couple of classes ago. I'll note here that your text shows how to get here from the control volume form of the momentum balance. So if you're reading along at home, you'll have seen a different version of this derivation, but we're going to get to the same place. Okay. It's just that by using the total derivative, we're going to get there a lot faster. So we're going to start here. We're going to say that the sum of the forces is ma, right? And the mass we'll write as rho dx, dy, dz, right? So if we have some differential fluid element, the mass of that fluid element is the density times the volume. And the acceleration, remember, of a parcel of fluid is given by the total derivative of velocity with respect to time, right? dv dt. Right, uppercase v, uppercase d v over uppercase dt. And so now if we plug in our definition of the total derivative, right, from a few classes ago, we end up with this form, right? So sum of the forces is the mass times the acceleration. And we have the simplified or the condensed form of this, right, in terms of our vector operators. I won't say simplified because I know maybe this doesn't appear that simple, but it's definitely condensed at least, right? It takes up less space. And now the question is, what are the forces that can change the momentum of a fluid particle? So can anyone give me a force that can change the momentum of a fluid particle? Everything we learned in the last section still applies. So just one force. Yeah. Pressure, right? Pressure can definitely change the momentum of a fluid particle. And so we're actually going to track pressure, we're going to track gravity, and we're going to track shear stress. Okay. So we're going to have surface forces like pressure and viscosity, and body forces. In this case here, we're going to use gravitational body forces. And so we're going to put these into Newton's second law and look at force per unit volume. So we're going to divide through by dx, dy, dz. And we'll end up with this expression. Rho g minus grad p plus grad dot tau ij, and we're going to talk about this thing, is equal to rho times the total derivative of velocity. So I just want to start, right? So this is the influence of gravity. This is the force per unit volume due to gravity, force per unit volume due to pressure, force per unit volume due to viscosity. Again, this is brand new to you, so we're going to talk about this over the next couple slides. And acceleration of a fluid particle. These two, this is exactly what we had for, or this is the same as what we had for static fluids. So if you were to go back to your notes from chapter 2, we developed an expression for force on a fluid element where if there's no velocities, right? So if all these V's are 0, we'll see that this thing, the viscous shear force, this also depends on velocity. So in a static fluid condition, this would be 0. And we would get back to this as our force balance, which is what we had in chapter 2. Now you might be wondering where the negative sign went. Remember we said grad P was minus gamma delta Z. And that negative sign is because this G here, this is a bold G, this is the gravitational acceleration as a vector. So this points in the negative Z direction, and that gives us another negative sign that would get us to exactly where we were in chapter 2. Okay. So we've seen this before, right? This is chapter 2. We've seen this before, at least last class and the class before, right? That's acceleration of a fluid particle. We have to deal with this thing, the viscous stress term. One thing to note, as it's written here, this thing is a tensor, which is like a super vector. And I really just want you to see this concept because it's actually a little bit illuminating as to what a vector is. And so that should you see something like this in the future, you kind of know where to turn. But the idea is that this thing, this tau ij, is a way of keeping track of all the different directions and orientations in which we can have a shear force applied to the fluid. So this thing has 9 components that are organized into one quantity. So we have 9 components that we just put into one thing. In this case, written out as tau ij. So yeah, so it's sort of like a super vector. A vector has 3 components. A tensor has 9. And what that tells us is, like, let's look at this tau on the x face. This is telling us, this is keeping track of the shear stress on the x face of the fluid acting in different directions, either x, y, or z. And that can be different than the shear stress acting on the y face in its different directions, x, y, and z, and different than the shear stress acting on the z face in x, y, and z. And we need a way of keeping track of all of this. And mathematically, the way we keep track of this is in what's called a tensor. Okay. we're going to simplify this into the form that we're going to use for a Newtonian fluid. So we're not going to be dealing with tensor calculus in this class. But if you see that tau ij, or if you see that tau term, in general, that's a tensor. So this is called a viscous stress tensor, and it describes viscous forces that are acting on the three different XYZ faces of a unit cube of the differential elements of a fluid. And we need 9 elements because, again, those viscous forces can act on each face, can act in each of the 3 different cardinal directions of Cartesian coordinates. Right, so it acts on each of the 3 different faces. So that's the first subscript, and in each of X, Y, and Z directions, that's the second subscript of this tau ij thing. One thing, so again, just to reemphasize, our differential momentum balance, which is written here, is a vector equation. When we take the dot product of this thing, this del operator with tau ij, and we'll look at what that is for a Newtonian fluid, we end up with a vector. The dot product of del dot this tensor is just a vector. So this is a vector equation, right? We have 3 components, X, Y, and Z. Wasn't good. So for example, in the X direction, we have this expression, rho times the X component of gravitational acceleration, normally going to be 0, right? Minus dpdx, plus these components of the stress tensor, right? D tau xx dx plus d tau yx dy plus d tau zx dz is equal to rho times the total derivative of velocity with respect to time. Right, total derivative of the x velocity with respect to time. And you can see there are analogous expressions for y and z given in your text, this equation 4.35. And this expression here is valid for any fluid, but complex unless we simplify. So for example, we could apply this to a non-Newtonian fluid, right? So if we really want to understand what's going on in the Oobleck videos that we watched earlier in the class, we could use an expression like this to do that analysis. We just have to write out something for these tau xx, yx, and zx. Somehow relate these back to velocity, and then we'd be able to do, for example, CFD of Oobleck or something based on this kind of an expression. All right, so I just want to take a breather for a second and talk about this term again, and have you all discuss it. So let's just look again at this expression, right? So this is the x direction momentum balance. We said that these are the forces, right, on the left side, right? Some of the forces is mass times acceleration. Just to remember where we came from, I want to ask you, or I want you to discuss, what does this term mean? So this is v du dy. Now remember, this is the x component of the force balance, right? This is the x component of the momentum balance. And the x component of velocity, we're going to write as u. If you look at this term, why is there a v? So I want you to discuss what is this term. Give you a minute or two just to discuss with your neighbors. So what's going on here? Please. All right. I see a lot of discussion coming down. Not all, but a lot of it coming down. Who has an answer for me? What is that term? What does that term mean? Nice to hear. Yeah. It's the movement in the y direction, right, which is the velocity in y times the gradient of the velocity of the x velocity in the y direction. So times the rate of change of the x velocity in the y direction. And we would get this by tracking fluxes through the faces, yes. But this has something to do with net flux. Another, yeah. So this is not a y direction movement. That's a good question. This does not come from tracking momentum through the x face, which is maybe a hint as to what this thing is. Someone else have some insight into what this expression is, Tata? It's like the water bottle flying through the upper surface of the control volume. So what do you mean by that? I'm going to flip it around a little bit. It is the y velocity advecting x momentum. Okay, this is the y velocity changing the x momentum within the control volume. Okay, and this has to do with the amount of the net amount of x momentum that's being carried into and out of the control volume across the y faces. Okay, so this doesn't come from tracking y velocity through the x face, as you point out, right? This comes from tracking x momentum that's lost through y faces, right? Through the y faces, the top and bottom faces of our control volume. Okay, and this is exactly analogous to what we saw in the control volume form, and then I tried to illustrate with a water bottle. Imagine throwing it across the room. So this is, again, x momentum advected by y velocity, right? And this is x momentum advected by z velocity, right? And then this one, what's this one? X momentum advected by x velocity, right? This is the one that people don't tend to have much trouble with. But again, watch out for these, right? When you're writing out the terms of this expression, these are the ones to be careful about. Okay. And again, this is exactly analogous to what we saw in the control volume form. All right, any questions on this? Yes. So the question is, in homework and exams, are you going to be given momentum, velocity, solving for something else, or are you going to be solving for velocity? Sometimes you will be solving for velocity. Sometimes you will be solving for something else. Okay. Yeah, so this form of the expression where we have this tensor quantity, I don't expect you to be able to do much with this unless I give you exactly what this tensor quantity looks like. When we get to the Navier-Stokes equations, where we're going to essentially simplify this for a compressible Newtonian fluid, then we're going to get to a set of equations that I do expect you to be able to manipulate to solve for velocity in some cases, as well as to manipulate and find other terms of the expression. Okay. Yeah. Yeah. Fully using the Navier-Stokes equations to solve for a wide variety of different kinds of velocity fields, that's more graduate level fluid mechanics. But there are some essential flows that I do expect you to be able to solve for. So, and you'll get some of that on your homework. Okay, so one simplification, right? So we're going to follow basically the same playbook that we did for mass, momentum, energy in CV form and for mass in differential form. We're going to simplify, right? We're going to look at appropriate simplifications of the equations that we derive. So one is for inviscid flow. So if we ignore viscous stresses, right? So if we say that all those tau things are just zero, then we get a major simplification of momentum balance. This is known as Euler's equation. So now we have this part, which you should remember from fluid statics, or which, if you go back in your notes, you would find from fluid statics, equal to rho times the total derivative of velocity with respect to time. Right. So we've gotten rid of all that messy stuff. This is used to study what's called inviscid flow, or flow where we can assume that there is no effect of viscosity. So if there's no viscous friction, we've already looked at an equation where there's no viscous friction, right? What equation did we develop where there's no viscous friction? Bernoulli, right? So you can actually use this. You can use this expression to rederive the Bernoulli equation. And it's actually a classic way that the Bernoulli equation was derived or developed. Yeah, so this is major simplification. So if I ask you something about Euler's equation, this is what we're discussing. Okay. Well, let's get back to that viscous stress term, because we're going to see that that is critical in most of our understanding of the types of problems that we're going to be solving in this class. So for the special case of a Newtonian fluid, the viscous stress tensor is given by this ugly expression. And I don't expect you to be able to recall this from memory or something, okay? But we can write tau ij in this form for a incompressible Newtonian fluid. And now if we take this and we plug it back into the momentum balance equation that we had previously, and we resolve that del dot tau ij operator, again, the definition of which is beyond the scope of this class, then we end up with this expression for example, for the x direction momentum balance. This I definitely do expect you to know. We have our again, our gravitational force. Generally, Gx is 0, right? The x component of gravitational force we normally assume is 0, minus dp dx, right? The derivative of pressure in the x direction, plus mu. Remember, this is our Newtonian fluid viscosity from day 1 or 2. It's coming back. Mu times second derivative of u with respect to x, plus second derivative of u with respect to y, second derivative of u with respect to z, equal to rho times du dt, right? Capital du dt. Yes.
In other directions, like say we had the y direction, we just replace the u with v and then z.
Yeah. So in the y direction, this would be rho gy minus dp dy plus mu d squared v lowercase v dx squared d squared v dy squared d squared v dz squared is rho. This would be partial v with respect to t plus u partial v with respect to x, v partial v with respect to y, w partial v with respect to z. Yes, Tata. Yeah, so if you remember, we had it is just the first row. Yeah, it's just the x direction. Yeah, exactly. Exactly. Yeah. When we take, because we're taking the del dot, we're actually taking del dot tau ij. So we're taking like the dot product. We're taking the dot product of the del operator with this tau ij. Yeah, but again, I don't expect you to be able to reproduce that. So that's why it's not up here. Yes. That's x squared. So this is, I mean, this is how we write the second derivative operator, right? So this is the second derivative of u with respect to x. This is how we write it. And it is x squared. Yeah. We write it d squared u dx squared, not d squared x. It means the second derivative. Yeah, yeah. Math is hard. Yeah. And here, the main thing, again, to just keep track of is mind your U's and V's and so on, right? This, yeah, that's often where, again, I see the most mistakes, especially once we get down to here, right? You get so used to writing out U when you're considering the X direction momentum balance that, you know, just kind of your brain goes on autopilot and you fill in U's down here. So that's where you see the most mistakes. Okay, other questions? Yes. Yeah, if you go through the definition of what tau ij is and your simplification will end up dropping out, that too will end up dropping out. And we end up just with this expression here. So we didn't actually lose it. We didn't lose it too. And we're assuming that this mu is isotropic in this case. So it is the same. So we have the same value in all for shear force applied in all directions. Yeah. I didn't want to dwell on how to do tensor calculus because, again, that's not something I expect you to know. Yeah. If you want to go through it, I'm happy to. We can sit down and go through the math of delta tau ij or graduate fluids, right? If you're really want to know where this comes from or what we can do for non-Newtonian fluids or something, then I'm happy to talk to you about grad school. Okay, but this is the form of the expression that we want to be able to use. And so let's just summarize our progress so far. So we have mass balance, sometimes also called continuity. For incompressible flow, we get this simple form: del dot v is 0, or du dx plus dv dy plus dw dz is equal to 0. All right, so we get the simplified form. And again, in this example, like if we consider we have some differential fluid elements, this is basically just telling us that if we have the flow slowing down in the x direction, then it has to be speeding up in the y direction in order to make sure that mass is conserved within that differential, within every differential fluid element. We just developed the momentum balance, rho g minus grad p plus grad dot tau ij is equal to rho times total derivative of velocity with respect to time. And for Newtonian fluid, we've written out the x component of this in terms of our second derivatives of velocity of the velocity field and our Newtonian viscosity mu. So if we combine the our form of the momentum balance for a Newtonian fluid with the mass balance for an incompressible fluid, then what we end up with are called the Navier-Stokes equations. So basically, these are the Navier-Stokes equations. So and the momentum balance or the force balance piece of the Navier-Stokes equations written here from kind of like a popular science article about about turbulence in fluids. With some corrections, they made that sign error that I warned you all about, the minus grad p that was missing. It was also a little confusing what was a vector or not within this expression. So a few corrections. But these Navier-Stokes equations then relate the mass, the density of the fluid times the total derivative of the velocity field to the forces that are acting on the fluids, right? Some of the forces is MA. And that viscous stress that del dot tau ij resolves into this form here, mu del squared V, or mu times the Laplacian of the velocity field, right? If you remember from heat transfer, we deal with Laplacian of temperature quite a bit, right? Del squared T. And for a and so for that vector v, this is what that del squared operator looks like. So if we're considering the momentum balance in the x direction, we ended up with d squared u dx squared plus d squared u dy squared plus d squared u dz squared. And so these are the momentum equation parts of the Navier-Stokes equations. And now remember, we combine this with, right, this is really three equations in one, right? Because this is a vector equation. And so in 3 dimensions, we really have 3 components of this to worry about, x, y, and z. When we combine this with the continuity equation, right, del dot v is equal to 0, we have 4 total equations in the Navier-Stokes equations, right? Momentum, x, y, and z, plus continuity, del dot v is equal to 0. So we have 4 equations, and we have 4 unknowns, right? We don't know the pressure, right? We don't know the pressure field. We don't know the velocity field in x, y, and z. So 4 equations, 4 unknowns, seems like it should be easy. Yeah. Yeah, so the question is, what is, the question is, what is and is not a vector? I mean, so the whole expression is a vector, meaning the whole thing has to resolve to a vector, right? If we take dv dt, right, this is just a vector, right? Yeah. So in this form, this is just the this is the convective acceleration term, right? So remember when we wrote this out as all of our terms, we had in the x direction, for example, this was u du dx plus v du dy plus w du dz, right? So this resolves to a vector when we go through the whole operator. This resolves to a vector. The gradient of a scalar field is a vector. G is a vector. And the Laplacian is a scalar operator. And if we apply that scalar operator to a vector, we get a vector. Right, del squared does not make a vector. That's correct, yes. And this is written out in x, y, and z components, which is generally going to be the most convenient form to start from in your text, just as we had it on the previous slide. Yes. So yeah, so the full, when we say Navier-Stokes equations, really properly, we're talking about 4 equations, x, y, z momentum plus continuity. That's correct. Yeah, so I should have put continuity on this. That's actually something I need to fix. Yes. That's P. So for an incompressible fluid, remember, rho is a constant, right? So rho is something that we measure offline and then we know it, right? So so rho is not going to be a variable for an incompressible fluid. Yeah. We will consider the case of rho being a variable in chapter 9. Okay. All right, 4 equations, 4 unknowns. It seems like it should be totally solvable problem. Yeah, here we go. When paired with continuity, del dot v is equal to 0, we have 4 equations. So the question is, this should be easy. But there are some issues with this, aside from just the nomenclature and the math and doing all of that. We don't have a general solution to the Navier-Stokes equations. We, in general, cannot always find a solution to the Navier-Stokes equations. So even though it's 4 equations, 4 unknowns, it's not always solvable. And so some of the issues here are turbulence, right? So we're going to talk quite a bit about turbulence in chapter 6, and then again in chapter 7, and the implications of turbulence on our ability to find solutions for these equations. But there's also like a just general mathematical problem with these equations, which is that we cannot say with mathematical certainty that solutions to the Navier-Stokes equations always even exist, right? So not only can we not find them necessarily because of the influence of turbulence, which just makes things complicated, but this set of equations, we don't know that a solution always exists. And this is the subject of something called the Millennium Prize, which is a prize in mathematics. So there are mathematicians still actively currently looking at these expressions, trying to determine if, we can say that solutions to Navier-Stokes equations always exist. So it's like $1 million prize if you want to give it a go. Yeah, $1 million to prove or give a counterexample of the statement that there should always be a solution to the Navier-Stokes equations, essentially. So these equations have been known in some form for about 200 years. So history puts the first developments of a set of equations that would become what we know as Navier-Stokes at 1822. So we're at just about the 200th anniversary of the development, or the beginning of the development, of the Navier-Stokes equations. Stokes here, who played an integral role, was barely just a few years old in 1822, and he would play a pivotal role in defining the equations as we write them down today. But still, we're talking about a set of equations that's nearly 200 years old, and we have a very basic question about what's going on mathematically. So like Terence Tao is probably the greatest living mathematician. This is a problem that he's been working on in the past 5 to 10 years or so. And we still have no answer to this basic question. So was there going to be a question? No. Okay. So I thought you were about to raise your hand. All right. So what do we do here, right? So in the face of this like mathematical uncertainty, not only mathematical complexity with all of these arcane vector operators and so on, but there's no guaranteed solution to anything with these equations. So what are we going to do? Well, the first thing we're going to do is simplify, right? So we're going to take these expressions and we're going to simplify them for certain cases where solutions do exist, and then you'll solve for some of those cases, for example, on a homework. And we will solve for those in class as well. So the classic example will be pressure-driven flow between either two flat plates or in a round tube. And we'll see in that case, most of the terms of the Navier-Stokes equations will drop out. We'll get something that's fairly simple, or at least I want to say fairly simple if it doesn't appear simple to you, but simpler than the full Navier-Stokes equations to the point where we can develop a solution to it. We'll see that we'll develop an expression for the parabolic velocity profile within a tube. It's going to form the basis of much of our work in chapter 6 when we're considering flow in pipes. This is actually a visualization done by someone in the lab where I did my PhD, actually, where they're looking at a flow in a round tube, laminar flow, called laminar flow in a round tube. And they're visualizing it using dye that they basically activate with laser light. So they put down a stripe of laser light at time 0, which activates just a small stripe of fluorescent or glowing dye at time 0, and then they watch it get pushed down by pressure over time. And what you can see is it starts out right nearly as a continuous stripe with everything in the same x location, right? More or less. We're looking at this just after t0. And now as time moves on, we can see that dye be advected downstream in this parabolic velocity profile, which we'll derive. Another thing that you can see here very clearly is no slip, right? So we said that no slip condition generally holds. And some of you actually came up after class and asked me, well, what would happen if you had dye or something within the fluid? Well, the dye, some of that dye would remain, that dye which is closest to the wall would remain essentially at the initial X component, the initial location where it was activated. Now, eventually, for real dye, right, these are molecules that are diffusive. And so eventually some dye molecule, which was exactly at the wall, would get jostled around by thermal forces and move away from the wall into one of these other streamlines and get moved downstream. So this would not persist forever because of the effects of diffusion. But it does nicely illustrate the no-slip condition. And I should note, this is true. This is a channel which is probably about the width of a human hair. This is done with a microscope. So no-slip condition holds even down to very, very small length scales. So that's one case. We're going to use simplifications, right, to understand the Navier-Stokes equations and do something with the Navier-Stokes equations. The other thing we're going to do is turn to empirical relationships, right? So, you know, mathematicians having trouble with the Navier-Stokes equations, that's fine, but we're engineers and we have to build real things, right? So, and we know that, you know, while there may be some, you know, mathematical questions about whether or not solutions exist, we know that, you know, real fluids do real things, and we can turn to the behavior of those real fluids to help develop some empirical relationships, so that we can deal with more complex flows, right? So, for example, this is showing a jet exiting into a stagnant fluid, quiescent fluid, where we can see this jet break down into this mess, and this is turbulence, right? So what we're seeing here is characteristic of turbulence. So if we look, and we'll talk quite a bit more about this in the coming weeks, but one of the key features of turbulence is this structure that you see here. So you can see that there are not only there are some big vortices here at the edges, but you can almost see those big vortices breaking down as we move, right? This flow is coming out this way. You can almost see those big vortices breaking down into these little tiny vortices as we move down within the flow. That is characteristic of turbulence. You can also see it dissipating as we move out towards the stagnant fluid. So dissipating from this region of really high energy, lots of fluctuations, lots of vortices, so therefore lots of contrast in this image, in the center of the stream, dissipating into the stagnant fluid below. That's another characteristic of turbulence, the dissipation of energy through the motion of these vortices within the fluid. So in the face of this kind of complexity, we will be unable to develop analytical solutions to the Navier-Stokes equation, right? So here, we're going to develop analytical solutions to Navier-Stokes equations to discuss these things. But when we have turbulence, we're going to be unable to develop analytical solutions to Navier-Stokes equations. But instead, we're going to turn to empirical relationships to define how key quantities in here relate to the velocity field. And we can use that to develop approximate forms of what happens within turbulent fluids. And we can use those kinds of relationships as the basis for models and computational fluid dynamics simulations. So if we wanted to simulate this in computational in a computer, we can do so on a laptop machine now without having to consider the full details of what's going on here. Okay, any questions on Navier-Stokes or momentum balance? Okay, so we're going to end it there for today, just a minute or two early. On Wednesday, we're going to come back to energy balance and develop a differential form of the energy balance. Thank you all.